The exponential functions are easy to distinguish because they look a little bit like a child's playground slide. In this case, the x coefficient usually will control the steepness of the slide, and the 3 will control the vertical translation. So to get to our first question, to find the x-intercept, we have to make y equals to 0. And by rearranging, we get to the point where e to the 2x is 3. And as we're trying to look for the value of x, we need to ln both parts. So ln, first of all, the left-hand side, and also ln the right-hand side. From natural logs, you might need to remember that ln e to the 2x is really 2x. In other words, you might think of it that the ln e just disappears and you're left with the 2x. So we conclude that 2x is equal to ln 3. So x is going to be equal to ln 3 over 2. This answer could be simplified if I look at it like this, and I'll say a half ln 3. So if I've just separated the half, I use my laws of natural logs, and remember that ln 3 therefore is to the power of a half, which ends up being ln root 3. Alright, what about the y-intercept? So we substitute the x for 0, and that just ends up to be 0. So e to the 0 minus 3 is equal to 1 minus 3, which is equal to minus 2. That's our y-intercept. Oh, that we have to show algebraically that the function is increasing to show that its function slope is increasing. That means its derivative is increasing. So dy dx is going to be 2e to the 2x. Now, e to the 2x is always greater than 0 for all x. So that means that dy dx must be always greater than 0 for all x. And thus, therefore, we can conclude that the function is increasing. Now, there are two parts to see. One of them is just to find the second derivative of this x, and the other one is to explain why fx is concave up for all x. Let's just work on that one first. Find out this. So we know that dy dx is equal to 2e to the 2x. So the second derivative will be 4e to the 2x. Now you need to explain why fx is concave up, which means that we're going to visualize our child's slide as a smiley face. That's going to be concave up. Concave up is sometimes known as convex, and it basically means that the tangents are below, and therefore the slopes go from negative to positive, which means that the slope function is increasing when dy dx, that means the second derivative, is greater than 0, or you might say is positive. And we can see here positive, and you can see from our second function that 4e to the x is always greater than 0 for all x. So we have proved, therefore, that the second derivative is always positive, and that means that our function must be always concave up because the slope is always increasing. Okay, so just please note that if you have a slope which is a curve which is concave down, then the second derivative must be always negative. And if you've got a function or a curve which is concave up, the second derivative will always be positive or greater than 0. Just need to remember this. And for D, we are told to use technology to help us draw this graph. And so I've just used Desmos, and you'll see that we have said that the y-intercept here is going to be -2, and the x-intercept is going to be ln √3. And it's like a fairly steep child slide. And so why is -3 a horizontal asymptote? To explain why is -3 a horizontal asymptote, that means that y values never go below -3 or never touch y -3. You're going to show that this function can never go below 3. So what you want to do is to show that is substituted into that function all the way up to -infinity. Then e to the 2x, whenever you substitute the x into a number, will always go to 0. And as our graph is supposed to e to the 2x -3, then if we make e to the 2x 0, we end up with getting y is equal to -3.